Okay, so question number 8. Is beryllium dichloride polar or nonpolar? Okay, so let's first write down a Lewis structure for beryllium dichloride. So to write down the Lewis structure, we first need to calculate the total number of valence electrons for this molecule. So beryllium has 2 valence electrons that can participate in the bonding, and chlorine contains 7, and since there are 2 atoms of chlorine, we multiply this by 2. So now if we were to add these values together, we get a total of 16 valence electrons. So now let's draw beryllium as our central atom. And if we were to draw 2 single bonds to the chlorine, it would look like this. And we can also show all of the lone pairs on the chlorine as well. So let's just draw them in. And if we count out how many electrons we've drawn so far, where each bond contains 2 bonding electrons, then you can see that we already have our 16 valence electrons in this structure. So to find out whether or not this molecule is polar or nonpolar, step 1 would be to just find the difference in electronegativity So this can be delta En between chlorine and beryllium to see if the bond is polar or nonpolar. Okay, so let's look up the electronegativity values. For these 2 atoms. So the delta En of chlorine and beryllium. So beryllium has an electronegativity of only 1.5 and chlorine's is 3. So the difference between the two would be 1.5. So therefore, the bond is polar since our electronegativity difference is greater than 0.4 but less than 1.69. So since we know that the chlorines are much more electronegative than our beryllium, we can draw dipole moments going towards the directions of the chlorines. But if we look at the Vesper shape of this molecule, so let's also look up Vesper table. And if we were to analyze our Lewis structure, we can see that our central beryllium atom has 0 lone pairs and 2 bonded atoms. So its molecular shape is linear. And already we can see in the picture that the two dipole moments in chlorine will cancel each other out, since there are no lone pairs on the beryllium to offset the dipole moments. So since we have a linear structure, this means that the dipole moments do cancel each other out. So therefore we have a nonpolar molecule. So this is an example of even though we have polar bonds involved in the molecule, we can still have a nonpolar molecule if the dipole moments cancel each other out. So we can call this as a zero net dipole moment. Which makes it nonpolar. Okay, so let's see what the junior tutor said. So it looks like they fully explained what a polar molecule is when two atoms do not share electrons equally in a polar covalent bond, and when there's a slight positive and slightly negative charge on each of the atoms. And they also have some polar molecules as an example as well. So water, ammonia, hydrogen sulfide, and ethanol. So a polar covalent bond exists with atoms with different electronegativities, for example, HCl. And they have the definition of nonpolar molecules. When atoms sharing a polar bond arrange such that the electric charges cancel out. Okay, so yep, so when you have polar bonds and they cancel each other out, you can have a nonpolar molecule. And they also have, if there's a nonpolar covalent bond, electrons are evenly distributed. Okay, so when the electronegativity difference between two atoms is less than 0.5, it's considered nonpolar. Okay. And they say even though the only truly nonpolar molecules are those formed with identical atoms, so like diatomic gases and the noble gases as well. And they said that this is a nonpolar molecule since it is symmetrical. The dipole-dipole moments are cancelled out, and it has a linear shape. Okay, so this solution is